I always think whenever I see southerly and stuff like that, I always think of like a weather forecast here. This one's going to use the same two formulas. We're going to use E as F over Q, and then electric field is negative change in electrical potential over R, right? Okay, so electric field exerts a southerly force on 1.3 newtons on a 780 microcoulomb charge. So notice we've got the force of the charge, so we're going to figure out our electric field. 1.30 newtons south, right? Divided by, that's, yeah, okay. And then 780 E minus 6 coulombs, right? So let's do that. 1.3 divided by 780 E minus 6 is 1,666. It's a lot of sixes. All right, here we go. Okay, and that's newtons. It's newtons per coulomb. Okay, and this is south. All right, so let's see. Okay, so what is the change in potential if you displace yourself 5.3 meters to the north? Here we go. Okay, so all right, here we go. So let's figure this out, right? So this is our formula here, right? We want to find the change in potential. So our change in potential, right, or negative the change in potential is just the electric field times our distance, and the change in potential therefore is opposite of E times delta R, right? Okay. So now we're, we got to figure this out, right? We've got this southerly electric field, so we put it in here. Ultimately, we just got to multiply this, right? But hopefully we'll get, our goal is to get that plus there, right? You want to get that last half point, right? Okay. So anyway, I'm going to give you another way to think about this, but let's do it mathematically first, okay? So I go opposite of 166.6 repeating, right? That's newtons per coulomb south, right? I'm just plugging in stuff here, right? And then I'm going to go north, right? So north, if you recall, is negative south. So I'm going to go negative 5.3 meters south. Okay. All right, here we go. And so we want to find our change of potential. I'm going to multiply those, right? And I get 88333333. Positive 88333. Okay. And this is Newton meters per coulomb, which is a joule per coulomb, right? Which is the same as a volt. Okay, so how did I get the positive? Well, mathematically, it's negative and then a negative, and there it is, right? That might not work for you, so let's just think about this, right? If that electric field is south, let's draw a picture of this, right? If the electric field is south, here's north, here's south. Okay, that must mean that north is more positive and south is more negative. Does that make sense? Okay, here's why. Because if I put a positive charge here, a positive charge would go away from the positive and toward the negative. It would be a southerly electric field, yes? Okay, so this is what I do. Honest to God, the math really doesn't do it for me. The math works, but this is what I do. I draw a picture, and I say, look, if there's a southerly electric field, okay, that means that positive is in the north, negative is in the south. Here's why. Because if this is a small positive charge, it will start to go south because it'll be repelled by this and attracted by this. Now, think about this. If we want to know what is our change in potential. Well, if we go north, it's a positive change. Why? Because we're heading toward the positive, away from the negative, okay? Or we're going from something that's more negative to something maybe that's less negative, okay? Any shift toward the positive is a positive change in potential, okay? So this is what I do, honest to God. I really struggle to do the math with like minus and then make that minus and stuff. For me, I just draw a picture. Look, if the field is pushing me south, if you go against a field, you're increasing your potential. If you go with the field, you're decreasing your potential. Now, that's all well and good, and we were blessed to have a positive charge here. Keep in mind, if it's a negative charge, you've got to answer the question in terms of positive charge, and that gets a little bit challenging. All right.